Hi, everyone. The plan for today is to try and wrap up chapter 13. So we're going to move through three subsections, but don't let that stress you out. We're just going to touch on a few highlights. And if you go and check the actual textbook, you'll see that these are three pretty short subsections. 13.4, where we are jumping in today, discusses the interpretation of confidence intervals. And we'll mostly look at the idea of saying, let's assume that we've calculated a 95% confidence interval. What does that actually mean? Now, we have talked a little bit about the interpretation, but let's dig just a little bit deeper. So we've been talking about constructing a confidence interval for a population proportion. And we do that by taking the sample proportion, calculating standard error, calculating a z-star value, etc. But what we end up with is a range of values, some lower value to some upper value, and that whole range of values makes up our confidence interval. What do we know when we look at that range of values? Well, in some sense, we don't know a whole lot, because that confidence interval that we have calculated, maybe it does, maybe it doesn't. We are not really sure whether that confidence interval calculates or contains the true population proportion. Maybe it does, maybe it doesn't. So why do we do it then? Well, let's take a step back and consider the hypothetical of repeating this experiment over and over again. So perhaps a good way of thinking about this is, I assign a project to each person in class. Each person goes out, collects a sample of 100 students at TCU, and asks each student in their sample whether they were born in Texas or not. So everyone's going to come back with a slightly different proportion. First student may tell me their proportion is 34%. The next student may tell me their proportion is 36%. Next one might tell me their proportion is 31%. Everyone's going to get potentially a slightly different number, and that means everyone's going to get a slightly different confidence interval. So we're going to get a whole bunch of p-hat values, a whole bunch of different sample proportions. And if each of you constructs a 95% confidence interval, then what that confidence level tells me is what proportion of you would have confidence intervals that capture the true proportion. So 95% of you are going to have confidence intervals that contain the true value. Now remember, we don't know what the true value is, but whatever it is, 95% of you will have intervals that contain the true value. But 5% of you will have confidence intervals that are duds, that do not contain the true value. This is the important thing we always have to keep in mind with a confidence interval. We don't know whether or not it contains the true value, but we do have a degree of confidence based on the level that we've specified, which in other words means we know if we use this method over and over and over again, what proportion of the time is the method going to work well. Here's another way of illustrating that. Each of the vertical lines here represents a confidence interval. And each of the lines is a 95% confidence interval. And what you can see is there's a horizontal line here at the true value P, and 19 of these 20 confidence intervals include the true value P. But there's one confidence interval, the red one, that doesn't include the true value P. This is what happens whenever we construct a confidence interval. If it's 95%, that's the same as 19 out of 20. That means out of every 20 confidence intervals you construct, roughly 19 of them will contain the true value, but 1 out of every 20 is not going to contain the true value. And as long as you keep that in mind, you can make really good statistical statements and reach valid conclusions with confidence intervals, as long as you recognize you cannot ever say anything with 100% certainty. We always have samples that deviate far from the population just due to sampling variability. So let's look at one example. Let's say we had a survey of 1,520 US adults. 68% of them say they use Facebook. Now, you should go and check the math here, but for this result, we know that the standard error is 0.012, and you can construct a 95% confidence interval that ranges from 65.6% to 70.4%. So the correct way to interpret that interval is therefore to say that we are 95% confident that this confidence interval captures the true proportion of US adults who use Facebook. Does that mean that we definitely know between 65.6 and 70.4% of US adults use Facebook? No. But we have 95% confidence that the truth is in that interval. However, it could be one of the 5% of confidence intervals that are duds. But we have no ability to know that without actually doing a census of the whole population. Now, we'll dig in a little bit and do some extra math, and we're now going to define a new quantity, although you've been calculating it all along, known as the margin of error. That is something that helps us measure the accuracy of a specific confidence interval relative to the confidence level. So I hope this first formula on this next slide looks familiar, that everyone's seen. If we're doing a 95% confidence interval, you're going to take p hat plus or minus 2 times the standard error. In a more general instance, if we're not specifically doing 95%, but if we're doing some level C%, you know, corresponding to that C%, you're going to calculate a value Z star, and then for the confidence interval, you're going to multiply that by the standard error. So this quantity that in general we add and subtract, the Z star times the standard error, we call that the margin of error. And so the margin of error is really just measuring for us how big our confidence interval is, because it's telling us how big a step we take to the left if we subtract the margin of error, and how big a step we take to the right when we add the margin of error. And there are many quantities, not just proportions, where this general type of formula holds. You'll see in the coming weeks, we're going to look at population means and regression slopes and constructing confidence intervals for them. But the general formula is always going to be, we're going to have some estimate, some value calculated from a sample trying to get at what the true population value is, and the confidence interval formula will always be plus or minus some margin of error. So that's a very general way in which we calculate confidence intervals. Now, the margin of error is useful in that it tells us how big the confidence interval is. So the illustration here, adding 3 standard errors and subtracting 3 standard errors, that corresponds to a 99.7% confidence interval. So in this case, the margin of error is 3 times the standard error. And so that gives us a sense of how much precision we have, right? If the margin of error is large, we don't have a lot of precision. But if the margin of error is small, we do have a lot of precision. Now, if you were doing a 95% confidence interval, your margin of error would be 2 times the standard error. Relative to that, you could increase or decrease the confidence level. But increasing the confidence level increases the length of your confidence interval and subsequently also increases the margin of error. Decreasing the confidence level will decrease the length of the interval, but therefore it also decreases your margin of error. Just remember, margin of error is always relative to the confidence level. Okay. Now, let's do 2 quick examples here. Firstly, let's say someone reports the results of a poll. They took a sample of 4,654 adults and then reported that their results are subject to a margin of error of 1.5%. Now, there's something we need to understand about polling here first. The convention in polling is to construct 95% confidence intervals and to calculate the margin of error assuming the true value of the proportion is 0.5. So if we know that, we can figure out how this margin of error value was obtained. Because remember, margin of error is just given by z star times the standard error. So for a 95% confidence level, we know our z star value is equal to 2. And our standard error will be calculated as the p times the q divided by the sample size, square root of that entire quantity. And let me punch that into my calculator here. And when I take the square root, I get a standard error of 0.0073. So this means my margin of error is given by 2 times this 0.0073 value. And if I do that multiplication, I get 0.0147 or 1.47%. So if we round that to 1 decimal place, that's where the 1.5% comes from. Let's do one more example here. Let's assume someone conducted this poll and they asked people how often they read a newspaper. And we found that 52% of people said they hardly ever or never read a newspaper. If we were to construct a 90% confidence interval based on the sample proportion, what would our margin of error be? Now, in this case, our sample proportion p hat is 0.52. Our z star value for a 90% interval is 1.64. And we can also calculate our standard error. So we'll use our sample proportion here. We always use that when it's available to us. And let's see what this calculation gives us. So 0.52 times 0.48 divided by 4,654 and take the square root of that, we get 0.0073 or 0.7%. So our margin of error is going to be 2 times the standard error, in this case 2 times 0.7%. So our margin of error here is 1.4%. And we will do some more margin of error examples in our live Zoom session tomorrow. The last thing we're looking at today from section 13.6 is how to determine the sample size you need in a specific situation. So here we're flipping the question around. Here we are saying we specify beforehand both our confidence level and the desired margin of error. And we want to calculate what sample size will result in us having that desired level. So effectively what we have to do is we have to take the equation for margin of error and we have to solve for n in this equation. Now I know perhaps algebra is just a distant memory to you, so I'm not going to expect you to do this off the fly. Instead, I'm just going to give you the formula if we flip that around. If I take that same formula and I solve for the sample size, then the sample size that you need in any given situation can be calculated as p hat times q hat multiplied by the square of z star over the margin of error. So to figure out what sample size you need to specify the desired margin of error, you need to specify z star, which comes from your confidence level, and trickily, you need some sample proportion. We'll talk about that more in a moment. But you're going to do this calculation, and whatever value you get for n, typically it's going to have some decimal part. Well, you're going to round that up to the next integer. So, for example, if you find that n is equal to 134.21, you will round that up to the next integer, and that will tell you what sample size you need in a specific setting. Now, the difficulty here is this calculation is to figure out what sample size you need for the purpose of calculating your sample proportion. So it's a little bit circular because it says we need a sample proportion to figure out what sample size we need to calculate a sample proportion. The workaround is, in many instances, people will do a small pilot study. So they anticipate that they're going to have to collect a lot of data. But to figure out the sample size they will eventually need, they'll run a small study with maybe 50 or 100 observations and use that pilot study data to calculate a preliminary value of p hat and plug that into the formula to figure out how many additional observations they need to collect. There is one other workaround here. There's a quantity that's known as the most conservative estimate of sample size. Here the formula is 0.25 times the square of z star over the margin of error. So this calculation, it does not need you to have some initial value for p hat, which is great, and you implement it in the same way. You do the calculation and then round up to the next integer. But the most conservative estimate has the downside that it can give you a result requiring a much larger sample size than what you will actually need in practice. And I will illustrate this again tomorrow during our live Zoom session when I do some examples of this. But this brings us to the end of chapter 13. So we'll do some more examples on that tomorrow. Also, tune in tomorrow because we'll have a conversation about what your test will look like next week. Thank you, everyone.